So welcome to our last week of Chemistry 30, where we are going to be talking about organic compounds, and we'll be talking about a couple of other ones that we weren't able to last week. Last week we were talking about aliphatic hydrocarbons. Now, if we think about the ones that we were dealing with last week, something like maybe there's propane, methylpropane is an example of an aliphatic hydrocarbon, or even here we have ethene or propene, is an aliphatic hydrocarbon. So these are chains. So just long chains of hydrogen, carbon. You can have other things in there as well, but we classify those as aliphatic. This week, we're going to start off by talking about aromatic. Aromatic compounds contain this very specific structure. This is called a benzene ring. Now, this benzene ring is special in that it doesn't react like we would expect something like maybe propene to react. Something like propene would react with bromine, and bromine would go colorless. It undergoes what's called an addition reaction, and bromine is added on either side of that double bond. Now, benzene does not do that. So that tells us that empirically, it doesn't actually behave like it has double bonds. And that's the history of this structure, where they knew benzene was made up of 6 carbons and 6 hydrogens, but they didn't know how it went together. Then this Kekulé guy, he said he had a dream where he dreamed of a snake eating its tail. And from that dream, he was able to come up with this structure, where we have 6 carbons, 1, 2, 3, 4, 5, 6. That's not a very good hexagon. But alternating double bond, single bond, double bond, single bond, double bond. And then 6 hydrogens bonded in that way. So we have this ring. And that's kind of what benzene, what they predicted its shape to be. Now, crystallography showed this later on. However, we know that it doesn't react like it's unsaturated. There are double bonds here, but in reality, it doesn't react like it has double bonds. And that's why we often draw it this way, a hexagon with a circle inside, because these electrons in those double bonds are actually what are called delocalized electrons. So they're shared amongst all of those carbons. So this is the structure for benzene, and you might see it those different ways. You might see C6H6, you might see it as an alternating ring with double bonds, or you might see it as a hexagon with a circle inside. These are all different ways to communicate an aromatic compound. Now, anything with this present is an aromatic compound. So model glue, methylbenzene, has a benzene ring, it's aromatic. Mothballs has 2 of these, it's aromatic. Here's a key compound in organic synthesis, 1, 2, 3. It has 3 of these structures, it's aromatic. TNT has 1 of these structures, it's aromatic. In order to be aromatic, it needs to have a ring like this present in its structure. When we name aromatic compounds, it can either be a parent chain, so we can have something like this, maybe 2 groups coming off of it. It can look like that. So it can be a parent chain, or maybe we have something like this, and it can be a side chain. Now, if it is a parent chain, the way that we name these is the parent chain is benzene. The other rules are the same. So if you think back to last week, we have a 1 carbon chain, that's methyl. We have a 2 carbon chain, that's ethyl. We're going to go alphabetically, so ethyl's going to go first, because E comes before M. And we also want to number it, so any side chains have the lowest number. So we go 1, 2, 3, 4, 5, 6. So this would be 1 ethyl, 3 methyl, benzene. So if it's a parent chain, the parent chain is benzene, and we follow those naming rules on any of those side chains, just as we would with any of the aliphatics last week. If it is a side chain, so now my parent chain is this, 1, 2, 3, 4, 5. So it's a 5 carbon chain. My parent chain is pentane. I don't really have a name for something that goes this way and something that goes that way. That's why the parent chain is pentane. So if it's a side group, my parent chain is pentane, and then we call it phenol. So if it is a side chain, it's called a phenyl group. Parent chain, it's benzene. Side chain, it's phenyl. The other rules are still the same. So I'm going to number from the left because I want that side chain to have the lowest number possible. And so that's 2-phenyl pentane. So 1-ethyl, 3-methyl benzene. So benzene if it is the parent chain, phenyl if it is a side chain. So that's how we name and we draw aromatics. Now, one thing you do need to be careful of is if it is maybe not drawn like that, you might sometimes see something like C6H5 attached to the side. That would be the same thing. So we have our benzene ring, and it only has 5 hydrogens because we need to take one off so that we can actually attach to it. But those are aromatic compounds, how we name them and how we draw them. Another group we're going to look at this week are organic halides. Now, these are very useful chemicals. Teflon, a non-stick coating on pots and pans, is an organic halide. When we think about CFCs, so a lot of refrigerants, things that are in our refrigerators. This week, there's this mini documentary you can watch if you want about chlorinated hydrocarbon, CFCs, and how they were destroying the ozone. But these organic halides, they have a lot of useful properties. They persist for a very long period of time. Now, we recognize them because they have halogens attached to them. So in order to be in these groups, anything from group 17, those are the halides. So that's fluorine, chlorine, bromine, or iodine. If those are attached, that makes something an organic halide. We name organic halides using prefixes. So if I have I guess here I'll draw a 2-carbon chain. So we have hydrogen, we'll draw a Cl here, Cl here. So we name it the same. We name our longest chain. So this is a 2-carbon chain. That would be ethane. We name organic halides with prefixes. So Cl, we would use the prefix chloro. So this would be chloro, and because there's 2, this would be dichloroethane. We do still want to identify which carbons they're on. This molecule doesn't matter. I can go left to right or right to left, but this would be 1,2-dichloroethane. Maybe we have a aromatic compound with things like this on. Maybe I have Br and I have F. So if we think about alphabetically, B comes first. So this is bromo. And this is fluoro. My parent chain is benzene, so it's benzene. Now B comes first, so I'm going to start at the B. 1, 2, 3, 4, 5, 6. So this will be 1 bromo, 3 fluoro, benzene would be the name of this organic compound. So we name organic halides with prefixes. Now, organic halides are still relatively nonpolar. They have relatively low intermolecular forces and relatively low boiling points. However, because they have these different groups attached to them, they are slightly polar. So they are maybe a little bit more soluble than the nonpolar hydrocarbons that we've been looking at previously. They do undergo more reactions. Now, we're not going to talk about reactions this week because we don't have time, but they do undergo more reactions because you have things with different electronegativities attached to these compounds. But these are a very useful class of compounds that maybe we don't necessarily know their long-term effects. There has been some articles recently about a lot of the CFCs that we replaced with compounds that were slightly different but not totally different. And now there is some thought that maybe these are also destroying the ozone layer in different kind of mechanisms. But yeah, so these are the organic halides. We name them with prefixes. So chloro, fluoro, bromo, iodo is how we would name those. Another group is an alcohol. So alcohols contain an OH. Now this is not a hydroxide. This is a molecular OH. We call this a hydroxyl group. So we could have something like propane, and we can attach an OH to it, and we can have propanol. Now that OH can be attached there. That would be propan-2-ol, or maybe the OH is attached here. Then that would be propan-1-ol. But the OH, the alcohols, contain a hydroxyl group. This group is great. This now makes this molecule polar. And it also, if you think about the OH, means that it's capable of hydrogen bonding. If you think back to some of these ideas in chemistry 20. So that means that the intermolecular forces are a lot higher. So alcohols will have higher boiling points. Something like ethane has a very low boiling point. Something like ethanol is going to be higher. Even just looking at those two, ethane is a gas, ethanol is a liquid because there are more intermolecular forces present and it's capable of hydrogen bonding. This polar region also allows an alcohol to dissolve polar things. So it dissolves well in water. You might have heard of like adult beverages which have 5% ethanol in them. So they are able to dissolve in water. And they also, because they have this non-polar region, are also able to dissolve non-polar things. So alcohols make excellent solvents and are used a lot for that purpose in industry. Now, as these molecules get bigger, so if we think about something like ethanol, so a 2-carbon chain with an OH, or we think about something like 1, 2, 3, 4, 5, 6, ethanol, or whatever, maybe hexanol. We'll go hexanol with an OH, 1, 2, 3, 4, 5, 6, and an OH, 1, 2, and an OH. If we compare these, so if we compare solubility, this is going to be more soluble. This will be less soluble. Now this is more soluble because it's shorter. As this molecule gets larger, there's this region of non-polarness, which is not very soluble in water. However, so very short alcohols are more soluble than very long alcohols. This one would have a higher boiling point, hexanol. This one would have a lower boiling point. Now they both have hydrogen bonding. So they do both have hydrogen bonding because they have that OH. However, hexanol is higher because it has greater London dispersion forces because it's a larger molecule. So we can compare alcohols in that way, or we can compare alcohols to things like that are the same length but with different functional groups. When we name alcohols, so you might have caught on already, but we name alcohols with a suffix. So here I have a 1, 2, 3, 4 carbon chain. So that is bute. And the way that we name alcohols is with the ending, we attach "ol" at the end. So butanol is the name of that alcohol. Now we do need to number it, and we do give that alcohol priority. So this is 1, 2, 3, 4. And the way that we identify the location of that OH is again with a number. So this would be butan-1-ol. Now this could be different. So if you think back to last week in isomers, I could have butan-2-ol, and that would look like this. So the number tells us where that OH is. So butan-1-ol, butan-2-ol. There is one exception, so one just to know. If we have a benzene ring with an OH attached, this is called a phenol. So it's a phenol if it's attached to an OH. So that's kind of its own little rule. Phenol if it's an alcohol with a benzene, if it's an aromatic alcohol. But this would be butan-2-ol. The ol because it has an OH, the 2 because it's on the second carbon. The bute because it's a 1, 2, 3, 4 carbon long chain. Now we could also have polyalcohols. So this is ethylene glycol or antifreeze. Think about naming it. It's a 2 carbon chain, so it's ethane. And because there's 2 OHs, we would call it a diol. So polyalcohols we name by using a di, tri, tetra, etc. at the end. But we do also need numbers with which carbon they're attached to. So this would be ethane 1,2-diol is the IUPAC name of ethylene glycol or antifreeze. Another group, so you'll notice that we're doing lots of groups this week. You might have to pause and go back or replay different sections as you're working through the assignment. Now these are carboxylic acids. So these are always at the end of an organic compound. And that's because a carboxylic acid is a very special group. It is a COOH. You might remember these when you were talking about acids and bases. These are organic acids. Some acids are not organic, like H2SO4 is not an organic acid. In order to be organic, it needs this carboxyl group, and it's a very specific group. It's a carbon that has a double bonded O. We call that a carboxyl group, and we have an OH, a hydroxyl group. And that makes our carboxylic acid. So carboxylic acid has this very specific structure where it's a C double bonded to an O, double bonded to an OH. That makes it a carboxylic acid. Now you can recognize some carboxylic acids around the home in the name. If you see ic acid, that's a sign that it's a carboxylic acid. So acetylsilic acid, acetic acid, citric acid, oxalic acid are all examples of carboxylic acids. Name carboxylic acids, it's at the end. Now, like alcohols, carboxylic acids are capable of forming hydrogen bonds. However, they can form even more strong hydrogen bonds because of this double bonded O that's also attached. So if I had a carboxylic acid or if I had an alcohol, a carboxylic acid is going to have an even greater boiling point than an alcohol because it can form more diverse hydrogen bonds because of this double bonded O. So carboxylic acids would be higher than alcohols. When we name carboxylic acids, so I'll draw a 1, 2, 3 long carbon chain. Here's a double bonded O and an OH. So when we name carboxylic acids, we still use the pro, etc. So this would be propan to identify the length of the carbon chain. The way that we identify it's a carboxylic acid is with the ending oic acid. So propanoic acid is a 1, 2, 3 carbon chain with a carboxyl group attached to it. So that's propanoic acid. Now, we don't need numbers because the carboxylic acid will always be where we start. There's nothing else that can attach on one side of that carbon. It will be a straight chain from there. So propanoic acid will always start at the carboxylic acid, and so we don't need to use numbers for carboxylic acids. If I had side chains, so here's, when I look at this one, I have I guess I need a side chain on there. There we go. So if I go 1, 2, 3, 4, so this is butanoic acid. So butane because it's 4, oic acid because it's a carboxylic acid. And then on that third carbon, so here I have a methyl group. So this would be 3-methyl butanoic acid. You'll notice that this side chain does not get the lowest number, so it's not a 2 because I need to start where that carboxylic acid actually starts. So that's 3-methyl butanoic acid is the name of that carboxylic acid. One last group is an ester, and an ester is what we get when we react an alcohol with the carboxylic acid. This ends up with something in the middle of the molecule, which is this ester linkage. If you think about alcohols, they have an OH. If you think about carboxylic acids, they have an OH attached to a C double bonded to an O. When we form esters in what's called an esterification reaction, we produce water. So there's this condensation reaction where this water is removed. So this water is removed from there. Then we're left with this molecule connected to this O that was previously connected to an H in that carboxylic acid. So we can take an alcohol, carboxylic acid, join them together, and we get what's called an ester. Esters are very volatile, so they vaporize easily, and they also generate a whole bunch of different aromas. So you can use different alcohols and different carboxylic acids which just smell like chemical, but by mixing them together, you can make pineapple, apple, strawberry. You can make a lot of artificial smells, which is used in things like perfume, shampoos, etc. So when we name and draw esters, so let's first look at an alcohol. So we'll look at the alcohol methanol. Methanol is a 1-carbon alcohol. I don't need a number because there's only one OH. And let's look at propanoic acid as my carboxylic acid. So I have a 1, 2, 3 carbon chain. There's my double bonded O and an OH. And then the rest of these H's to make these carbons happy. So I have methanol and propanoic acid. When they form an ester, so I link them together by removing this water. So I'm left with this C. So there's 1 carbon. And then I'm left with this O, this carbon double bonded to an O, and the rest of this 3-carbon chain. So this would be an example of an ester. When we name esters, the alcohol and the carboxylic acid are very important for the names because the alcohol becomes the start. So if it's methanol, the start of my ester name would be methyl. So whatever the alcohol is, we take the OL and we change it to ol. My carboxylic acid is important for the second part. This would become propanoate. So it was propanoic acid. I changed the ending to O8. So methanol and propanoic acid form the ester methyl propanoate. So the alcohol becomes the start, carboxylic acid the end. So methyl propanoate. Let's maybe look at one more ester. So I'll maybe draw this. And there's an O attached to a carbon, double bonded O8. And then 1, 2, 3. Sure. So when we are identifying, if we're given something like this and we want to name it, it's important that we identify which side is the carboxylic acid side, which side is the alcohol side. The separator is always going to be that O that links the two halves together. The carboxylic acid side will always be this side with the double bonded O. So this is a 1, 2, 3, 4, I think I meant to draw 5. 5. A 5 long carboxylic acid. This would be pentanoic acid. And then when I look at my alcohol, I have a 1, 2, 3 long alcohol with an OH coming off the second carbon. This would be propan 2-ol, because that's where my OH would have been, is the name of my alcohol. So when I name the ester now, so this would be propan 2-ol pentanoate. So if we do have a diagram like this, we need to split it at that O, identify which side is the double bonded O, that's our carboxylic acid side, which side does not, that's our alcohol side. So a lot of different things to name this week. It is a relatively busy week. You do have this video. Don't be afraid to pause, go back, use it as a reference as you're working through practice in your assignment. If you have any questions, feel free to communicate with me. But this is our kind of our wrap-up week for Chem 30. Good luck, and it was a pleasure being your teacher.